Exercise a02 is going to have us modify slightly the previous exercise that we developed in a01. Where I'm going to just, I kind of simplified thing here by already starting the modification. What I did is I copied all the files that we had in the previous exercise folder A01 into a new folder named A02. I now opened all of them with a text editor slightly different than Kwrite, but don't concern yourself with this, okay? The only thing that is new here is that I have the name of my file to allow me to switch easily between them. As you can see, I modified here things such as the headers, okay, and since my header is now a02.h, well, the pound define here has to be modified. A02 has to include a02.h, and if I go to the main, same thing, I have to include now a02.h. So very basic changes, that's why I did them offline and not in this video. Now what we are going to do is we are going to first ensure that everything is compiling. So there we go. Syntactically everything is fine, and since I didn't alter the code, well, if I run it, I'm going to have the same test harness than I had before. So I'm going to do that real quick. Run a.out, 5 employee, 1, 1, 2, 2, 3, 3, 4, 4, 5, social security number 5. Here is a display number 3, it's 4. Everything works still as it was working before. So we didn't break anything by this trivial little change of file names and stuff like that. That's what I wanted to verify. Now, back to the exercise description. The work we have to do here is to try to make things more dynamic, pretty much. Step 1 is saying that instead of having a fixed size array in my main, so let's go to the main.c file, I want now this to be pretty much a dynamically allocated array. And we want to ask the user first, how many employees do you want to handle? How many employees do you want to handle? Well, let's ask the question to the user. Do a scanf %d and read inside of our variable n. So by default n is 5. Okay, but I read here from the user how many employees exactly they want to manage. And then I'm going to declare my data as being a pointer on struct record s. And the next step, of course, is to allocate dynamically malloc. Okay, let's restart that. Malloc size of struct record s times n. I want to allocate enough memory to store an element of size struct record s. And of course, as soon as I do malloc, I need to ask myself, when will I dispose of this memory? In our case, it's relatively easy. When my program is about to finish, I'm going to free my data. And that's the moment at which I'm going to get rid of this array of this dynamical array, of structure of type struct record s. Okay, so we change a little bit of stuff in the main here. Let's save. Do we have to change anything elsewhere? Well, let's have a look. Let's have a look to a02.h. Well, the data structure definition is certainly the same. I'm accepting here parameter of type array. I refer you back to the chapter on arrays and pointers. Okay. I'll refer you back actually to the entire series 201, 202, 203 of module, because this is where we pretty much covered the fact that you can still use a data square bracket without size specifier here when you pass a pointer to the function. So this doesn't have to be changed. Then let's have a look here at our function themselves. My parameter is going to be different. My data in the main is now a pointer, but that doesn't show here in the parameter declaration. Therefore, all those notation I'm using here are also correct. Okay, once again, it's important that here you understand the similarities between pointer and array perfectly. Okay, because we're not going to go back over that. This is something we already covered, but this is something we are going to heavily rely on for the rest of this course. So let's try to compile our code. Couple of warning here that I missed. Implicit declaration of function malloc in main.c. So let me go back to main.c. I'm now using the malloc function. I need to include stdlib.h. Okay. Let's try again. Go back to the terminal, GCC again. Syntactically correct. Now, let's run it. How many employees do you want to handle? Well, let's do only 3. Employee 1, Social Security 1, 2, if I can type it, Social Security 2, 3, Social Security 3. Display all the employees. You see that we take into consideration only 3 of them. Which employee would you like to display? Let me display employee index 0. That's the first one. Perfect. So we have modified our code here so that we are now manipulating a dynamically allocated array of struct record s element. That's not the only thing we had to do. The second step also aims at making things more dynamic in our code. However, this time we want to make something different dynamic. We want to make the char, the string field inside of the structure record s, dynamically sized. Instead of having an array of 20 characters, no matter if your name is Joe or something that is 19 characters long, you still allocate 20 characters in that field, okay? Well, we want to get rid of that. We want to go to the point where we have just a pointer on char in that field. And then, as the user type a name, we're going to store it in a temporary buffer of an arbitrary size, for example, 30, assuming 30 is big enough to handle any last name that's going to be given to us. And then once we have stored it inside of this temporary buffer, we are going to measure the length of the string inside the buffer. It's not because your buffer is size 30 that automatically what the user typed takes 30 characters, right? So we use strlen to measure here the size of the string the user typed. We allocate dynamically a string of exactly the appropriate size. So if the user typed Joe as a name, we're going to allocate a string of size 4. And we copy into it the string that is held in our temporary buffer. Okay, so even though the buffer is of size 30, it's really important that you understand that if you have Joe as a string inside of a buffer of size 30, you have JOE\0. And when you do a str copy, these are the 4 only characters that are going to be copied into the newly allocated string. Once we are done, we put the address of this newly allocated string inside of the name field of our data structure, and we'll have to make sure that we deallocate it appropriately once we are completely done. So that's a little bit more modification than the previous step, okay? So let's go back to our text editor. Do we have anything to change in the main? No. Do we have anything to change here in our data structure? Well, I'm just following, okay, the indication in the exercise. I want name to be a pointer, which means name is occupying 4 bytes, all right? And there is no longer any room in name to store a string. Name is just going to store the address of another chunk of memory containing the name to be stored in that structure, okay? So the name itself is no longer part of the structure just has a pointer to whatever piece of memory will hold the string. So it can be variable length. It's a very classic way actually to store strings, of course. a02.c, well, once again, we go over the code and we try to figure out if this change is affecting our code in one way or the other. We iterate over all employee record. Well, this doesn't change. We ask here, I'm talking about employee number I, give me its name, and we scan %19s, a single word of maximum 19 character, into data index i.name. This is the problem. This is a problem because right now, data index i.name is a pointer. A pointer to what? A pointer to nothing. We never allocated any memory, so this is just a pointer that points to anything in memory. So if we try to scan and store at that location, we are going to cause our program to crash. So let's try things differently. Let's follow the pattern that is given to us inside of the exercise description. First, I am going to declare here char buffer 30. That's just an array of char that cannot hold more than 30 characters that is going to be used for me to just read something from the user. So I put here buffer. Once the user is done typing the name they want to give to their employee, I'm going to measure the length of that name. Int name length. And I'm going to do a name length equal strlen of buffer. Once again, it's important that you understand the answer is not always 30. Depends on what was typed. Once I know the length of the name, the user type, for example, 4, if the name was Joe, I'm going to actually do a malloc. So I'm going to say, what is the name of my data structure array? Data index a dot name equal malloc size of name length plus 1 for the backslash 0. Oops. Plus 1 here. And that's going to be it. And times, of course. I'm saying something stupid here. I was like trying to make sense of it, but okay. Sorry about that. Size of a char. This is what I want to allocate. Times name length plus 1. That makes a little bit more sense. Okay? So what I'm saying is that give me the size of one character, 1 byte, times how many characters I need. Name length plus 1. Semicolon. Now I have inside of data index I.name the capability to copy the string inside of buffer inside of that newly allocated string. And it's going to be exactly the same size. Okay? Enter. So let me try to space this out a little. I handle the name first, etc. Then I handle the social security number. Well, let's try to save. And we're going to try to compile to see if syntactically this makes sense, and then we'll test it. Syntactically, implicit declaration of function malloc, a02.c. Okay, same than before. Found include stdlib.h will come to the rescue here. I save my file, and I compile again. Compile works. Before I test it, let me go over the rest of my function and figure out if I need to modify anything because of this change of the data type of the field name inside of my struct record s. How do I display it? With a %s. Correct. How do I display the whole set of employee records? Just using display data at. Correct as well. Make sure this is saved. We don't need to recompile it since it has not been modified, but let's give it a spin and test it. How many employees do you want to handle? 3. Employee 0, name is 1. 1, 2, 2, 3. 3. Same test harness we use. It displays correctly. Okay, actually it doesn't display anything, sorry. Display employee 0. Well, consistent with bug at least. Okay, doesn't display anything. So what's going wrong? Well, let's go back to our code here and we're going to track down where this error can come from. You could start by tracking down the display. Okay, so display, because the display is what is obviously faulty on the screen, right? %s here, data index I, dot name. Nothing looks wrong with that. So if the display is not at fault, well, it's maybe the way that you stored thing that is at fault. So we're going to go here. This is where we do our storing pretty much. And we're going to revisit our code and make sure that everything is working. To make sure everything is working, there's just ways to display intermediary information from time to time. For example, here we have our buffer of 30 characters. We scan maximum 19 characters, store it in buffer. What about doing a little printf here? I just read %s, and I'm putting it between square brackets so that on the screen it will be very easy to see where the string starts and where it stops. And I'm displaying the content of buffer. So what I'm doing right now, I'm going blindly through the code, okay? And what I'm doing is pretty much the steps that you can apply to almost any problem to figure out what's wrong, okay? I'm not trying to assume anything. I'm just going blindly through the code, displaying some information. I'm trying to get more information about what doesn't work. How many employees do you want to handle? Let's say that. 1, I just read 1. So that seems to be more working, okay? 2, I just read 2. 3, I just read 3. But when I display all of my employees, once again, the name is not there. So it must be something really silly at that point, okay? I just double-checked that my buffer was read correctly. I can remove that printf now. I had an hypothesis. My hypothesis was something is not working here. Well, I displayed the result. Seems to be working all right. Well, what about we display then, knowing that buffer is okay, what about we display the content of data index I dot name, just to see if it's working right after we deal with it, but later on when I try to redisplay it, it's not working anymore. So that's my hypothesis. Let me stop this program here. Let's recompile and let's see how this hypothesis holds. I want to handle free employee 1. There we go. There's nothing at all there. So we don't have to search any longer. We know exactly that this is the part of the code that is not working. Well, let me re-examine this code. Is there something that I should have done that I didn't do? Yes. Independently of whether this is a bug, I never checked if my malloc worked. So if data index I dot name equal null, I should handle this error. I should display something like p error no memory available for name field. And if that was the case, exit the program with, let's say, return code -1 to just indicate something went wrong. Okay? Well, that probably didn't solve my problem, but this is something I should have done. So let me add this feature, compile to make sure it's syntactically correct, and make sure it doesn't cause any problem when we run. Employee name is 1. I just read blank. Type 1, etc. So it didn't solve my problem, but at least I added something that I forgot and that I should have added from the start. What else can go wrong? Well, I measure the length here of my string buffer. Just out of curiosity, printf. Actually, I just read a string of length. And I'm going to display %d here, \n of course. And I'm going to display name length. Once again, I'm doing this blindly, okay? Sometimes you will have better intuition about what's wrong in your code, and you look at the code and go directly to it. If you don't have such an intuition, you have to follow pretty much a pattern I'm going through here, which is testing, double-checking everything, okay? How many employees do you want to handle? 3, 1. I just read a string of length 3. O-N-E. And I just read, this is a display string, so this is a part that doesn't work. Okay, so we are zeroing in the error pretty fast here. We know that the call to strlen was correct. It tells me the length is 3 for a string reading 1, so that tells me that when I allocate my copy, I need indeed to do name length plus 1. Size of chart times name length plus 1 to account for the \0 character. And then what? And then I have here str copy buffer, which is my source of information pretty much, into data index I.name. So what is going wrong here? Well, maybe we misuse strcopy. Every time you have a doubt over one of those functions, man strcopy, and you have here, we're going to increase that temporarily, you have here the man page of the strcopy function. What does it say? It says that strcopy return a pointer on char. We never used that so far. The first parameter is the destination, the second parameter is the source. And it's going to copy the string pointed to by src, the second parameter, including the terminating \0, that's good for us, to the array pointed by des. The destination first, source second. Let us double check here. What do we have here? str copy, destination, source, reverted. And that's how you zero in on an error, okay? With practice, you look back at that code, you are going to see immediately that, yeah, you inverted strcopy, okay? We could have jumped to strcopy directly because this most likely, this is 99% of the time this is going to be that particular code what's causing the problem, okay? The malloc not being checked, this is a side benefit of reviewing your code rigorously. Even if you forgot to check the return code of malloc, when you are looking for an error, when you are reviewing your code and assessing it, if you do it like step by step instead of jumping directly to strcopy, you might be able to correct some side errors like this one as well. So let us get rid of all that debugging information. I'm going back here to the man page and I'm typing Q to get out of it. Then I'm going to minimize a little my terminal, and let me look at this code once more to make sure that I removed all the debugging information printf, which are going to be useless for now. So Recompile, execute. How many employees do you want to handle? 1, 1, 2, 2, 3, 3. Name is 1, name is 2, name is 3. Let's display information about employee number index 0. Name is 1, a social security number is 1. So we are pretty much done with this modification here, and this modification was completely focused here on this function data scan data, sorry, where we had to handle pretty much differently the allocation of memory. One last thing we need to do, and I almost forgot it, one last thing we need to do, we allocate here some memory for that string. So when are we going to get rid of it? Well, let's go back to the main, okay? Once I'm done reading my data, I'm going to use it, I'm going to display it, I'm going to display one of my employee record, and this is where I deallocate all the employee record. I cannot deallocate the array of struct record s before I clean everything that is dynamically allocated inside of those structure inside of the array. Okay, so that means that here I need to go over all of my element in the array. So this is going to be a counter-controlled loop. Okay, the size of the array is n. Of course, I++ to increment my loop. And inside of each, I'm going to free what? I'm going to free data index I dot name, because that is a string that was dynamically allocated. Once I'm done freeing all the elements of my loop, all the elements of my dynamical array, all the fields name inside of each struct record s inside of my dynamically allocated array data, my data actually, sorry, I'm going to just free my data by itself. So that's a hard rule. If you have a dynamical array of structure, each structures are one of several pointers that points to things that have been dynamically allocated, you always get rid first of the dynamically allocated elements referred to by fields of your structure, and then you get rid of the overall dynamical array. Okay, so this is a code here that is going to do this job. Let's save. Let's make sure we didn't introduce compilation error. There's a little one. Yeah, this is when I went back here and I was about to change and I decided against it. So I lesser than n. We could have written here lesser equal, we could have written here, what was I thinking? I was thinking something wrong anyway when I was about to alter that. So this is perfect as it is. Start at 0, I lesser strict than n, I++. Sorry, I was thinking like completely the wrong direction. So I'm going to save that file. Okay, what was missing is the lesser strict symbol. I'm going to recompile the whole thing. Now let's try to run it and see if we introduce a runtime error. 1, 1, 2, 2, 3, 3. Information is displayed back correctly, which is to be expected since that part of the code didn't change. And when we deallocate, we didn't apparently cause any runtime problem while deallocating. However, keep in mind that it is extremely difficult, since this is the last thing we do in our program. It's really difficult to establish, whether this has been done correctly. If we try to free a null pointer, we are going to have a crash, immediate crash. So that we would notice. If we try to free twice the same amount of memory, I would have to try it. I don't recall exactly how this compiler would react, but there's a chance that just like when you try to dereference a pointer that has an invalid value, if that pointer is null, your program crashes immediately. If it's not null, unexpected behavior. You don't really know, that your program just made a boo-boo, and you might be able to run for like 2 more days, that program without problem before you realize that there was a problem. Well, same thing with the free, okay? So some cases are easy to detect. It's not because our code executes without segmentation fault here that means that it's perfectly fine. However, given the easiness of that modification here, you can look at the code and try to double check analytically if I have problem pronouncing that in an analytical manner, let's say. You can try to check that way if your code is working, and due to the simplicity of the problem, that would be just as good as running it and testing it like that. Okay, well, we are pretty much done with this exercise. So I'm going to leave here on the screen the code that we modified in the main. And we are going to move on to the next exercise.